Hello everyone, welcome to Practically. We bring learning alive. Hope you all are doing good. So we are having today physics session. Topic is magnetic effects of electric current. One short session. Already many more math sessions as well as chemistry, biology completed, and this is physics topic magnetic effects of electric current. Let's wait for a few more minutes. Our friends may join. Hope you all have attended to the previous sessions, and then you have learned. So if you are having any doubts, just watch the sessions again, because in this one shot, whatever the syllabus that is there for your term 2, the whole chapters, the whole syllabus is covered in one single shot. Okay, whatever the subject it may be, like mathematics, chemistry, physics, as well as biology, right? I hope I am audible to each and everyone who are watching. If so, if it is audible, just respond. Yeah, am I audible? Just respond. Say just yes in the comments. Am I audible? Okay, fine then. I am starting the session. In the previous session, we have discussed electricity. Electricity are all the content with many more examples we have discussed. And in the same manner, I have brought up this session, that is magnetic effects of electric current. Right? In electricity chapter, we have seen that when electric current flows through the conductor, heat is developed, which we are calling as heating effect of electric current. All right, and based on that, we have seen many more applications in it. What is Joule's law of heating? What sort of applications are there based on heating effect of electric current? That another we have seen in the last lecture. In today's session, this is magnetic effect of electric current. That means when electric current flows through a conductor, what observations we can have. So that we are going to discuss in this particular chapter. Well, actually, this session, this entire magnetic effects of electric current in this chapter, it was just began, of course, with an experiment that we are going to discuss. Yeah, so these are the sessions that you have attended, and today we are having this magnetic effects of electric current, which is the last session of this one shot sessions. Okay, and apart from this maths, physics, chemistry and biology, you are having even coding also. Yeah, so these are the coding sessions. So 16th you are having even today one more session, style properties in CSS1, 8 to 9:30. Don't forget to watch, don't forget to attend it. Yeah, and one more session on 28th February, you can see here. Okay, these are the sessions, one short sessions, right? Yeah, so I said this entire magnetic effects of electric current, it's originated from it's an accidental experiment. So why I said accidental observation? Because that time Hans Christian Ørsted, he was conducting an experiment which is related to electricity actually, where it's not involved in the concepts of magnetism by then. Okay, so then there was a compass which is nearby the circuit when he was conducting an experiment. So then he has observed certain changes, certain deflections that's made by the needle in the compass when electric current is flowing through it. So that's what we are calling it as Ørsted experiment. So say I'm taking a simple electric circuit with some electrical components. Okay, so I have taken a simple electric circuit that consists of voltage source and a resistor. Let it be an electrical appliance, whatever it may be. Okay, and it's, if the circuit is closed, as we know that electric current will flow, let the current flow through the circuit is I. So the observation that's made by Ørsted experiment is when electric current is flowing through this circuit, then the compass which is there, it was just placed. Okay, it's not placed intentionally to observe the magnetic effects. He was conducting an experiment related to electricity, and there was a compass just nearby the circuit. When this electric current is passing through, I mean when he has closed the switch, when the circuit is closed, then electric current will flow obviously. Then he has noticed the deflection which is made by the magnetic compass. Okay, and then when this is turned off again, it has shown to the deflection, and I mean it just has come to the in the opposite direction, and it was stationary. So when there is a flow of electric current in the electric circuit, then the magnetic needle has shown the deflection, and whenever there is no such kind of flow of electric current through the electric conductor, then there was no deflection has shown by the magnetic compass. These are the observations. So finally he concluded the point what is, there is no magnetic field externally which is placed to influence the needle, magnetic needle. This is a magnetic needle which can be influenced by any other magnetic field, but there is no any other additional or external magnetic field that's placed here to influence it wantedly or intentionally, but still it has shown deflection. So deflection is made, that is true, and there was no external field or external magnetic field that's applied over here, that's also true. Then where that magnetic field has come over here, that's the point. So then he made a conclusion. Yeah, Avinash, yeah, hello Avinash, Ajay Vincent, yeah, hi Ajay. Sir, electron क्यों जीतागा? So what is that? Titanium. Okay, fine. Shabana, yeah, hi Shabana. Aman, hi Aman. Okay, fine. See here. So these are the points which are very true. One is, this is a magnetic needle that can be influenced by any other external magnetic field or any magnetic field, and magnetic field, external magnetic field is also not there. That's also true. Magnetic needle has shown the deflection when there is a flow of electric current in the circuit. It has shown nothing, I mean there was no deflection when there is no flow of electric current. So the conclusion here is, hope I am clear, hope my voice, everything is clear to each and everyone. Okay, so the conclusion here is, when electric current flows in the circuit, when electric current flows in the conductor, then magnetic needle has shown deflection. So this indicates this is influenced by the magnetic field which is produced due to flow of electric current inside the conductor. That is the conclusion. Electric current, when electric current flows through the electric conductor, magnetic field will be developed. That developed magnetic field is responsible for the deflection of the magnetic needle. All right. Yeah, Samia. Fine. So here, when electric current flows in the conductor, then magnetic needle has shown deflection due to magnetic field produced by current carrying conductor. So this is the observation that can be understood with the help of Oersted experiment. When there is a flow of electric current in the circuit, then magnetic needle has shown the deflection. It means magnetic field is developed, that's responsible for showing the deflection. When there is no flow of electric current in the circuit, there is no deflection that has shown by the magnetic needle. It means there is no flow of electric current, I mean there is no development of magnetic field. Okay, fine then. So here, now let's move on to the next one. Based on this experiment, further so many advancements, I mean with the help of this experiment, these concepts were developed to greater extent. Okay, so it may be like up to Faraday's laws or Lenz law or Faraday's experiment. So such kind of things were developed, and it has this discussion has taken up to the this topic, especially moving charges and magnetism, to a greater extent. Okay, even the same chapter you are having in class, you'll be having in class 12 also, with some elaborated derivations and much more concepts. Okay, fine then. So here, yeah, Bindu, good evening, Bindu. Magnetic field and magnetic field lines. So just now we discussed here. Hope my voice is audible and my screen is clear to each and everyone. If anything, any disturbance is there, just let me know. Okay, fine. If it is from my end, I'll just try to sort it out here itself. All right, here magnetic field and magnetic field lines. So what is meant by magnetic field? In lower standard also you might have learned. Okay, magnetic field is nothing but the region or the surroundings of the magnet generally, within which it can experience the magnetic force. That means, suppose if I take a magnet over here, okay, if I take a magnet, then this magnet, which consists of course two poles, let them are north pole and south pole, this can attract any other magnetic object or magnetic substance within the certain vicinity. Suppose if I keep the magnetic object over here, then this can be either pulled or pushed away, whatever. Okay, just depends on the nature of the substance, either attracted or repulsive force, since magnetic force is a repulsive, or I mean both repulsive and attractive force. So suppose if I keep here, let this is pulled by this magnet, like with the help of attractive force, and now in the next case I have placed the same object somewhere else here, but in this case it's not pulled by the object. So what does it mean? This magnet can experience the magnetic force only up to certain extent. So that certain extent within which it can experience the magnetic force, we are calling it as magnetic field. So simply I can say magnetic field is the region or the vicinity within which magnetic force is experienced. All right, it's the region okay, I am writing here magnetic field, sorry, okay, magnetic field yeah, the region within which magnetic force is experienced. Okay, so that region or that surroundings or that vicinity, which we are calling it as field region. What field here? Magnetic field region. Now that magnetic field, how can we represent? We can represent this magnetic field with the help of field lines, which we are calling them as magnetic field lines. So to obtain these general magnetic field lines, okay, we are having a simple activity. That activity you are aware of already, just I am giving a brief discussion related to that activity. So take a cardboard sheet. On the cardboard sheet, let it be a white one. This is just to understand it very clearly. And if you are keeping a magnetic, just take a bar magnet, place it on it. Okay. Now mark the poles. Of course, they will be there, north and south, and draw the outline of this bar magnet by using pencil. Take a compass. So keep the magnetic compass near this north pole, and then you can observe one thing here. The needle of this magnetic compass, which is having a south polarity, will be deflected towards the north pole, and this will be again north pole. Just mark this one. Okay, now lift the compass and place over here. Then you can notice again the needle of south polarity will be towards this marked point, as well as the opposite will be north. So like that, if you'll bring, and you can notice this structure, which means it can complete a line like this. So based on these magnetic field lines of a bar magnet can be shown like this, children. So they will be like this. The representation should be done very neatly and very carefully. Even if you are not mentioning the arrow marks, or if you are mentioning them in a wrong manner, will leads the deduction of marks. Okay, this is the representation of a magnetic field lines of a bar magnet. Magnetic field lines of a bar magnet will be like this. So here there are the properties or characteristics, whatever you can call, very important. Even many times in boards they ask this question. Write about the properties of magnetic field lines of a bar magnet. Okay, so see here, point number 1, they are continuous and closed loops. Magnetic field lines are continuous and closed loops. Point number 2, always these magnetic field lines emerge from north pole and merge at south pole. That means outside of this bar magnet, outside of this magnet, magnetic field lines are directed from north to south. So they will move away from north pole and they will merge at south pole. Okay, next, inside the bar magnet they will move from south to north pole, and magnetic field inside this north and inside the bar magnet is uniform. Okay, so one I said magnetic field lines are continuous and closed loops. Second one, these magnetic field lines emerge from north pole and merge at south pole. Third one, any two magnetic field lines will never intersect each other. That's very one of the very important point. What's that? Any two magnetic field lines will never intersect each other. They won't intersect. What will happen if they will intersect? See here, a simple explanation is there, easier one, an important one. That is, basically magnetic field is a vector quantity. It's a physical quantities. We are having some classification, segregation like vectors, scalars, tensors, like that. So then here this magnetic field belongs to a vector quantity. That means it will possess one direction at one single instant. At one instant, one direction only it will be having. Suppose if you take these two magnetic field lines, if they are intersecting like this, then at the point of intersection, at this instant, this field line may possess two directions here like this, but which is not possible. That's the reason why two magnetic field lines will never intersect each other. So magnetic field lines will never intersect each other. If they will intersect, at the point of intersection, the magnetic field line will possess two directions at simultaneously, which is not possible. Okay, very important one. Next, another one, the relative strength of these magnetic field lines will depends how close they are. That means if the magnetic field lines are closer together, then the field strength is high. If the magnetic field lines are far away from each other, then the field strength is low. So these are the 4 points which you have to write under the properties of the field lines of a bar magnet. Point number 1, magnetic field lines are continuous and closed loops. Point number 2, magnetic field lines, they will emerge from north pole and merge at south pole. Point number 3, any two magnetic field lines will never intersect each other, because if they intersect, then at the point of intersection, magnetic field line will possess two directions simultaneously, which is not possible. So due to that, that's why they won't intersect. All right. And next, these magnetic field lines inside, they will be moving from south to north. Remember it. Next, if the magnetic field lines are closer, then the relative strength of the magnetic field is high. The magnetic field, there it is high. If the magnetic field lines are far away, then the magnetic field strength is low. All right. So here this we can observe with the help of even another activity. Take a cardboard sheet. If you are keeping the bar magnet on the, just keep the bar magnet on the cardboard sheet. Sprinkle this magnetic resin. Okay. If you give a gentle tap onto the magnet, gentle jerk or gentle tap, if you tap gently that cardboard sheet, then the alignment can be observed very keenly, that can explain the same thing, how magnetic field lines are going to be aligned. Okay, all right. So this is about magnetic field. What is field exactly? How the magnetic field lines of a bar magnet. Okay, right. The next one. Okay, see then, magnetic field due to a current carrying conductor. So Oersted experiment has revealed that when electric current flows through the conductor, magnetic field is developed. We are having then different types of conductor, like we are having a straight conductor. Okay, we are having a circular loop, I mean circular coil also. You can say circular conductor. And we are having a solenoid. So our observations has to be made now based on, I mean, for these type of conductors, how magnetic field will be for the straight conductor. That means when current flows through the straight current carrying conductor, how magnetic field lines will be, and how the magnetic field lines will be for a circular conductor, and how magnetic field lines for a solenoid. That's what we are going to observe. Magnetic field due to a current carrying conductor. Alright, here actually to explain this direction of the deflection of the magnetic compass, we are having a rule, that is a Snow rule. What is this Snow rule? Suppose if I take an electric conductor in which electric current flows, take a compass. Okay, so now here this is the compass, let it be. If electric current flows in the conductor in the direction of south to north, see in Snow rule, south to north, S and N represents south to north. An electric current flows in the conductor from south to north, or if you will keep the direction of the electric current along the south to north, we can get to know by the help of this compass. Okay, and if the compass is held over the wire, then the deflection of the needle will be towards west. Current has to flow from south to north, and if it is held over the wire, then the deflection of the needle will be towards west. And suppose if it is going in reverse direction, then the deflection of the needle will be towards east. So this Snow rule we can use to determine the deflection of the needle when electric current is flowing through the conductor. And one more rule also there, that is Ampere's swimming rule, that you can have in in class 12. Okay, even now also Snow rule we are not having, but sometimes they are asking the deflection of the needle. Those questions will be there, objective type and all. So then this will help you out to find the direction of the magnetic deflection of the magnetic needle. All right, so magnetic field due to a current carrying conductor. Now we are going to discuss about field lines for a straight conductor, field lines for a circular conductor, and field lines for a solenoid. All right, so then see here, first one, magnetic field due to a current carrying straight conductor. Okay, so this can be explained with the help of a simple activity. All these activities are there in the NCERT textbook. While preparing for your exam also, refer your NCERT textbook. That will be the ultimate resource. Okay, I can say. Fine, then take a cardboard sheet. Through the cardboard sheet, just pierce the straight conductor as shown in the figure. And now complete this circuit here with the help of a switch. Okay, so now when electric current flows here through this conductor, so positive to negative, so it will flow from like this, positive to negative. All right, so now if you sprinkle magnetic resin, earlier I am showing before giving the connection here, that magnetic resin randomly, if you'll sprinkle here magnetic resin, Now when electric current flows through this, if you tap gently, then all this magnetic resin will be aligned in the form of concentric circles like this. So this gives a clear observation. When electric current flows through a straight current carrying conductor, then magnetic field lines, magnetic field that is developed on its surface will be in the form of concentric circles. Very important point. The magnetic field which is developed by a straight current carrying conductor will be in the form of concentric circles. The direction of the magnetic field can be explained with the help of right hand thumb rule. So here I did not mark the direction now. First, to mark the field direction here, you have to take the help of that's what right hand thumb rule. Okay, or grip rule also we can call it as. Now what is right hand thumb rule? First let us see. Okay, and then I'll come to here again. So this is right hand thumb rule. You can see the diagram here. Hope you are able to see the diagram very clearly. So this is the conductor. This is the conductor. Okay, this is the conductor and this is the direction of the current. If you are holding the conductor with your right hand in such a way that by pointing the thumb along the direction of the current, then the direction of the curled fingers, suppose if I am holding like this, okay, this is the current carrying conductor, and you have to keep your thumb finger in such a way that along it has to point the direction of the current. Then these curled fingers will represent the direction of the magnetic field. Very simple. So in this case, if you see, he has taken the conductor like this, and suppose if I say the direction of flow of electric current is, suppose if I say from here to here, I have to hold like this, and I have to keep the thumb finger along the direction of the current. Then this direction of the magnetic field is indicated by the curled fingers like this. So right hand thumb rule says that if we are holding a current carrying conductor with right hand in such a way that by pointing thumb finger along the direction of current, then curled fingers will represent direction of magnetic field. Okay, very important and very easy to remember. If you are holding the current carrying conductor, a current carrying straight conductor or current carrying conductor with your right hand in such a way that by pointing the thumb finger along the direction of the current, then the curled fingers will represent the direction of the magnetic field. Okay, how simple it is. So now I am going to obtain the direction of the magnetic field when a current carrying straight conductor you have taken. Okay, here I have taken a current carrying straight conductor. Okay, so this straight current carrying conductor is carrying current from top to bottom like this. Okay, so you have to hold the direction. This is the direction of flow of current, right? So you have to hold this conductor like this. This is one. I am holding like this. This thumb finger is along the direction of the current, downside. Then these curled fingers will represent the direction of magnetic field, which means here in this case magnetic field lines will be like this. Okay, see here, they are like this, so they will come like this. Suppose if the current is flowing in opposite direction from down to bottom, down to upside, bottom to upside, you have to hold this conductor like this, by pointing the thumb along the direction of the magnetic current. Then the magnetic field is indicated by the direction of the field curled fingers like this. So this is how you can apply right hand thumb rule to determine the magnetic field direction. Okay, now so this is about magnetic field due to a current carrying straight conductor. The conclusion here is magnetic field of a straight current carrying conductor will be in the form of concentric circles, and the direction of the magnetic field is explained, or obtained with the help of right hand thumb rule. Right hand thumb rule says that if you are holding a current carrying conductor with your right hand in such a way that by pointing the thumb finger along the direction of the current, then the curled fingers will represent the direction of the magnetic field. So that's how, like this. Okay, all right, then next one, field due to a current carrying field due to current through a circular loop. Okay, circular coil, these current carrying conductors will be of many types. Straight conductor we have seen, and circular conductor if you take, which consists of so many number of turns. In that number of turns, I'll take one loop, one single turn. So if I take the single turn, so this is the circular loop. The two ends of the loop are connected to the voltage source, and this is the plug key. Now when the circuit is closed, electric current will flow through the circuit. So this current will propagate like this and will return to the source like this. All right, so now here according to Oersted theory, we know that magnetic field is developed when electric current will flow through it. Okay, now here the electric current through the circular coil is flowing in this direction. So if it is straight conductor, we have seen excuse me, if it is straight conductor, we have seen how magnetic field will be for a straight current carrying conductor. Now if it is circular loop, how it will be? So here children, when magnetic field is when current is flowing through the circular loop, magnetic field is developed, and that will be in the form of concentric circles near the magnet, near the wire, just like this. And they will become curved when they are moving away from the wire, and they will become straight in the middle of the circular coil. Okay, so here how can we determine the direction? Again, just obtain the take the help of right hand thumb rule. So this is in this point one, in this point, if I take, this is the direction of the current, if I will hold like this, then here the curled fingers are wrapped in this direction. So magnetic field will be representation of a current through a circular loop. Okay, so see children, am I audible? Children, am I audible? Whoever are watching. Okay, fine. Hope my voice is clear and video is visible. All right. So when electric current flows through a circular coil, then how magnetic field will be? So it will be like this. Very, very important and easy too. Okay. So when electric current is flowing through the circular coil, near this coil, magnetic field will be in the form of concentric circles. So if you see near this, near here, they will be in the form of concentric circles. If you are moving away from the coil, then these magnetic field lines will become curved lines like this, and at the center magnetic field lines will be in a straight line. Okay, so here this magnetic field basically will depends on so many parameters. If it is a circular conductor, as I have taken one turn here, it depends on number of turns also. So as a circular conductors, when it consists of more than one turn, then more amount of magnetic field will be produced, and it depends on the point of point at where we are going to calculate magnetic field. Suppose if you are taking the point at which you have to calculate magnetic field a bit close to the wire, then magnetic field strength is high. When you are taking the same point a bit far away from the wire, that means current carrying conductor. So the current carrying magnetic field developed by the current carrying conductor will depend on some different factors. They are like amount of current flows through it. Suppose more amount of current is flowing, then more magnetic field will be developed, and more number of turns are there here, then more amount of magnetic field again. And if the point which you are considering at which we have to calculate the magnetic field, if you are considering it close to the current carrying conductor, then more amount of field, and if compared to the point which is far away from it. Okay, so based on these various factors, magnetic field will be depending, intensity of the amount of the magnetic field will be depending. So magnetic field due to a current through a circular coil, it will be like this. The magnetic field lines will be in concentric circles near the wire, and will be curved lines when they are away from the wire, and will be straight lines at the center. All right, so here it will depends on strength, depends on strength of current and number of turns majorly. Okay, very important. And even radius of the loop also. Okay, even here radius of loop also. All right, so these are the factors on which magnetic field lines, and this is how the magnetic field will be for a current carrying circular loop. Okay, right. Next one, magnetic field due to a current carrying solenoid. Solenoid is nothing but the current carrying conductor which consists of some number of turns, if it is wrapped in the form of helix. Okay, this is helical manner, or helix we will call. Okay, that's called a solenoid. So generally, when electric current flowing through this solenoid, then magnetic field developed is just similar to bar magnet. So for bar magnet, how magnetic field will be, we have seen. How magnetic field is, we have seen. Okay, for bar magnet, magnetic field lines are continuous closed loops, and they will emerge from north pole and merge at south pole. Okay, so those magnetic field representation of a bar magnet we have seen. Here solenoid, that which consists of some number of turns, and it is wrapped spiral manner. That's what we are calling it as solenoid. The magnetic field developed by the solenoid is just similar to the magnetic field developed by a bar magnet. Okay, so solenoid means a current carrying coil that is wrapped in the form of a helical structure or helical manner, or in the form of a helix, that we are calling it as a solenoid. Okay, so if the same thing, this is wrapped in the form of a ring type, that we will call it as a toroid. Now this is a solenoid which is wrapped in the form of helix or spiral manner. So let I is the amount of current flows when circuit is closed here. Okay, so according to I-stud experiment, when electric current is passing through it, then magnetic field will be developed. All right, Now here this field will be in the form of closed loops like this, children. Okay, suppose if I say this is south pole, this is north pole. So from inside the magnet, inside the magnet, they'll move from south pole to north pole like this. Okay, so this is the magnetic field representation for a solenoid, which is very similar to the magnetic field of a bar magnet. So here important point that you should notice is magnetic field inside the solenoid is uniform and it is parallel lines. Very, very important. Magnetic field inside the solenoid is uniform. Okay, right. So if you observe this pattern or the alignment of the magnetic field here, field lines here, you can just compare the same with the bar magnet also. Okay, you won't find any difference. So that's why I said magnetic field developed by a solenoid is just similar to the bar magnet, where the magnetic field lines are continuous closed loops. All the magnetic field lines emerge from north pole and merge at south pole. Okay, and here inside the bar magnet they will move from, inside the solenoid magnetic field lines are directed from south to north pole, and inside this magnetic solenoid magnetic field is uniform and there are continuous parallel lines here you can see. All right. Here also the amount of field developed or intensity of the field developed by the solenoid will depends on strength of current, will depends on number of turns, will depends on the air gap between each and every coil, each and every turn that existed in the solenoid. So these are the factors on which the magnetic field developed by a solenoid will depend. All right, fine. Let's move to the next one. Force on a current carrying conductor in a magnetic field. So we have seen so far, based on the Einstein experiment, when electric current is flowing through the conductor, then magnetic field is developed. So that magnetic field, how will it be for different types of conductors, like straight current carrying conductor, circular loop, as well as for solenoid we have seen. And now force on a current carrying conductor in a magnetic field. So when the current carrying conductor is placed in a magnetic field, then it experiences a force. It experiences force. That's what the activity is about. So this we can explain with the help of a simple activity, that is, consider a conducting rod just like an aluminum rod. Okay, place this aluminum rod between the poles of a horseshoe magnet. So why horseshoe magnet? Simple. To develop a strong magnetic field, we are taking here horseshoe magnet that consists of poles south and north named like that. Okay, now here this I am connecting the one end of the rod, I am connecting to a voltage source as shown in the figure like this. So this arrangement, See here, I have taken a metal rod or an aluminum rod that conducts the electricity. So this is connected with the help to the voltage source with the help of conducting wires like this, and this entire arrangement is placed over here with the help of a stand, and here this conductor is placed in the presence of a magnetic field which is developed by an horseshoe magnet like this. Okay, all right. So see here, children, whoever are watching, am I visible and audible properly? Just let me know. Sometimes it's becoming blur over here, that's why. Okay, fine. So see here, when this current carrying conductor is placed, conductor is placed in the presence of magnetic field, then this will be deflecting. That means this magnetic rod, this metal rod will deflect, will move either left or right, depends on the direction of flow of electric current, whatever. Okay, so generally this metal rod, to displace or to just to move it or to show the deflection, certain amount of force should be applied on it, but there is no external force is being applied. There is no external force that's being applied on this metal rod, but still it will show the deflection. So see here, that's what we can say that it can experience some force. How it's being experiencing, that's what we are going to understand with this, with the help of this activity. Let us take a metal rod. The metal rod is connected to the voltage source with the help of conducting wires, and this metal rod is placed in the presence of a magnetic field which is produced by the horseshoe magnet, and this entire arrangement is done or placed with the help of a stand as shown in the figure. Now when the circuit is closed, electric current will start flowing through it. Okay, so it will be flowing like this and will reach out the voltage source like this. So now we can observe that when electric current is flowing through this conductor, then this metal rod will show the deflection. Say it is right. Okay, so if it is let's say it is deflected to right here. Okay, and we'll get to know the direction of the deflection also. I'll tell you how can we represent the direction of the force experienced by the conductor. So now say right here, right deflection, let it is. That means this metal rod will be deflected towards right like this. Now if you reverse the direction of the current, that means if you reverse the terminals here, positive to negative, negative to positive, then current will propagate like this. So will return like this. Then you can notice deflection will be towards left. Okay, so in both the cases, before reversing the direction and after reversing the direction, metal rod is deflected. To deflect that, certain amount of force is required, but there is no any external force that is applied on the metal rod, but still it is deflected. What does it mean? It means that certain force is experienced. It's experienced by what? Because of the presence of magnetic field. So this activity concludes that force on this current carrying conductor will experience force when it is placed in the presence of a magnetic field. All right, so that can be explained with the help of this simple activity. Very, very important and easy too. Okay, so and another observation that you have to notice is when you are reversing the direction of the current in the conductor, then the direction of the deflection also reversed. Sorry, excuse me. Now I said the direction here can be determined. Direction of deflection, that means whether it is deflecting towards right or deflecting towards left, can be obtained with the help of a special rule that is called Fleming's left hand rule. That's called Fleming's left hand rule. So see here, Fleming's left hand rule states that, you can see the diagram here, it states that if you stretch the first three fingers of the left hand mutually perpendicular to each other like this, okay, in such a way that by pointing index finger along the direction of the magnetic field, center finger or middle finger along the direction of the current flowing through the conductor, then the force experienced by the conductor can be represented by the thumb finger. This is FLR, Fleming's left hand rule. What is that? If you stretch the first three fingers of the left hand mutually perpendicular to each other in such a way that by pointing index finger along the direction of the magnetic field, middle finger or center finger along the direction of the current, then thumb finger will represent the direction of the motion of the conductor or force experienced by the conductor. So see here, forefinger, you can remember like this. Field. Which field? Magnetic field. Okay, so F for field, forefinger, or you can say here index finger, whatever. However you remember, that can be. Next, center finger. It represents the direction of current. C, you can remember here C for current. Okay, C for center finger, C for current. F for forefinger or index finger, and then F for field. And then thumb finger will represent force direction. So see here, you can see the three fingers that are stretched like this. It states that if you stretch the first three fingers such as they are like forefinger, center finger and thumb finger of the left hand mutually perpendicular to each other, then just by pointing index finger along the direction of the magnetic field, then center finger along the direction of the current, then thumb finger will be representing the direction of the magnetic field. So that's what Fleming's left hand rule. All right. So see here, next, so there is a question that can be answered with the help of Fleming's left hand rule here. An electron enters a magnetic field at right angles to it as shown in the figure. Direction of the force acting on the electron will be dashed. So this we can solve with the help of Fleming's left hand rule. Just now we discussed Fleming's left hand rule states what? So in these three fingers, forefinger represents field, center finger represents current, thumb finger represents direction. Just apply the rule and you can answer this question. So see here, magnetic field is directed like this. So point your thumb finger like that. Electron is representing here, if I take this as a plane, it's showing downward. But actually we are following conventional current direction always, which is from positive to negative. But electron current direction is from negative to positive. Electron current direction is negative to positive. But conventional current direction is positive to negative. Okay, for solving all these things we have to follow conventional current direction only, not electron current direction. In this one, electron current direction is downward, but you have to take the conventional current direction. Electron current direction is downward, means conventional current direction is upward. So this is current direction, this is a field. Now see here, field I am pointing, index finger I am pointing this direction, and current upward, right? So current upward. Now see these are my three fingers. According to Fleming's left hand rule, I stretched. I pointed index finger, okay, in the direction of the field. You can see field direction. And now I have to turn this up without changing this. So like this I can. This now represents field direction. This represents current direction. And how my thumb finger now? It's pointed into this plane. See, if I keep like this, my thumb is representing this towards this plane. That means into it. So I can say here in this case, into the page or into the plane. That is the answer. Suppose instead of electron, if you are given any positive charged particle such as alpha particle like that, then you no need to reverse the direction of the current. Only for the direction of electron, only when you are given electron, then only you have to reverse the direction of current, since I said the reason why should you take electron current as well as conventional current, both are in opposite direction. All right. Next one, electric motor. So based on the previous activity, we have learned when electric current flows through the current carrying conductor, and if that conductor is placed in the presence of magnetic field, what happened then? It experienced some force. Now with the help of that concept, we are going to discuss the working of electric motor. All right. Yeah. Yeah, Ishan. Yes. So see here, what is this electric motor exactly? Electric motor is an electrical device that converts electrical energy into mechanical energy. Okay, now construction and working of electric motor, I'll explain with the help of a diagram. So see here, consider a magnetic field which is produced by the poles of a strong magnet. So this magnetic field will be basically directed from north to south. This motor consists of an armature. Armature consists of number of turns, that's a coil which rotates inside the motor. Okay, so here it's difficult to represent all the number of turns that are exist in the armature. I'll take a single turn and I'll call it as armature coil, and this is the armature coil which is named as ABCD, that's connected to brushes like this. Okay, and here I am taking an axle rod. So over which split rings are connected. So to these brushes, I will give electrical energy supply like this. Name this coil as ABCD. This is axle rod. Here brushes you can find B1, B2, and these are split rings. This is armature coil. So this is a simple arrangement of an electric motor. Electric motor is a device that converts electrical energy into mechanical energy. Just like how if you take the fan, inside the fan a single phase induction motor is there. Of course that is AC motor, fine, whatever, same operation is same. It will convert electrical energy into mechanical energy. It will take electrical energy as input and gives out mechanical energy as output. Okay, now here see, there is an armature coil which consists of some number of turns. In that turn I have taken only single turn, that I named it as ABCD. Okay, so when this the ends of this coil are connected to a contact carbon brushes, let there B1, B2, and this axle rod is inserted over here. You can find out an axle rod through which we can access the mechanical energy actually. And these brushes are further connected to the voltage source with the help of conducting wires as a plug key as shown in the figure. Now when the circuit is closed here, electric current will flow. Let the direction of the current flow here from positive to negative. Say this is the direction. Okay, now see how the mechanical energy is being produced. That means how this energy is being converted, we have to see. First we are giving input as electrical energy. Giving input as what? Electrical energy. Fine. Now electrical energy input is given. So electric current will be propagating. It flows through the coil. Okay. Here the motion observation should be done very carefully. So when this current is flowing here and the magnetic field is developed here, already this arrangement, this setup is placed in the presence of a strong magnetic field. All right, direction of the magnetic field from north to south. So now point the index finger along the direction of north to south, and now you can see this is A to B is the direction of what current flow through the coil. So I am taking the coil as like a plane like this. So inside, so like this, along this edge the current will flow. So this is my current direction. See, direction of current is I'll keep here like this. Direction of current is like this. I have taken onto the plane, just like an example. Okay, fine. Suppose if I say this is the coil, okay, so this is the coil. If I say here A, B, C, D, just like the book, 4 edges of the book, if you say, so along this edge now current is flowing. This edge is just indicating towards this plane. So in that direction you have to place the center finger like this. Now this forefinger represents the field which is from north to south. Center finger I kept in such a way that just pointing towards the plane. Then how my thumb finger is showing? Then thumb finger is showing downward. So here when electric current is flowing through this coil, that means conductor, as it is placed in the magnetic field, it experiences force here. How that force is experienced, in what direction? It experiences in this particular case downward. That means when this current flows through this AB side, I mean it will complete like A to B, B to C, C to D, then this AB side will start moving in downward. Since force is obtained here, I mean experienced here downward, so this will be pushed towards down. Then what about the CD? When AB goes down, CD will come up. The CD side will come up. So then as it has achieved the sufficient momentum, then the CD side, that portion will make another further rotation. So ABCD side, right? Now after half rotation it will be like this. D, C, B, A. So in the beginning it is ABCD. After half rotation, now that left side will become right, right will become left, ABCD. Okay, so now current will flow from D to C, C to B, B to A, DCBA. Earlier it is ABCD direction. Now DCBA direction. So current direction is reversed here. Direction of current is reversed here with the help of split ring commutator. So split rings or split ring type commutator is responsible for reversing the direction current for every half rotation. So now what will happen again? If DC will come here, again if you apply the Flemings left hand rule, then that will be further pushed. So these rotations will be keep on rotating until the flow of electric current is existed inside the coil. All right. So finally, as the result of the rotation here, the axle rod is attached here to the coil. As coil rotates, so axle rod is rotating here. That axle rod is a mechanical element. So mechanical element means we have given electrical energy as output and we got mechanical energy as output. Simple. So simple explanation of electric motor, very easy. When this current carrying, see this electric motor, if you are given explain concept and working of electric motor, simple thing that you have to do is, first you have to say on which principle it works, and then diagram, talk about its construction and come to the working and then give the conclusion. So electric motor is a device that converts electrical energy into mechanical energy. That's clear. It works on the principle of when a current carrying conductor is placed in the magnetic field, then it experiences force. Next, construction. It consists of an armature coil ABCD which is connected to axle rod with the help of contact brushes and split rings as shown in the figure. This entire arrangement should be, this coil arrangement should be placed in the presence of a strong magnetic field which is produced by the horseshoe magnets, say the poles north and south here, and the ends of these coil should be connected to the voltage source with the help of conducting wires or wires through a switch plug key as shown in the figure. That's about construction. Working. So when the circuit is closed here, current starts flowing through the electric conductor, conducting coil. Now say the direction of the current is from A to B, B to C, C to D, and then applying the Fleming's left hand rule, and here in this particular situation the armature coil having side AB will start moving down. When AB moving down, then CD will come towards up. Okay, and by the time the side CD, the coil will achieve or attain sufficient momentum to complete the further rotation. So likewise this direction of the current will be reversed for every half rotation, and such rotations will make that continuous rotations of armature coil will further rotate the axial rod. So thereby we can enhance the mechanical energy which is possible through the given electrical energy. So we can say electrical energy is converted into useful mechanical energy, and this kind of arrangement, that's nothing but these motors we can use in mixers, grinders, washing machines, electric fans, etc. So this is the way that you have to apply. How to remember Fleming's left hand rule, Aryan? Yeah, see, it's very simple. 3 fingers, 3 directions. Okay. First say 4 finger, and before that we are going to talk about 3 quantities here. 3 fingers, 3 quantities. One is magnetic field. You should remember at least these 3 fingers, first 3 fingers and those 3 quantities. So then I will give some blindfold to remember that easily. 3 fingers, right? 3 quantities are, one is magnetic field. Remember magnetic field. Okay. Second one current, C for current. Third one force or motion of the conductor, say force, F. Now see, in Fleming's left hand rule you have to remember this 4 finger, this is 4 finger or index finger. Remember it as 4 finger. Remember it as center finger. This has thumb finger. 4 finger represents field, F. Letter F. F represents field. So 4 finger represents field. Which field? Magnetic field. 4 finger represents magnetic field. C, center finger represents current. So center finger represents current. Thumb finger represents force. 2 over third one represents obviously force. Hope I am clear to you, Aryan. 4 finger represents magnetic field. Center finger represents current direction. Then thumb finger will represent the direction of magnetic field. Sorry, direction of force. Okay, hope I am clear to you, Aryan. Yeah, so this is about electric motor, how it works, construction, okay, and applications. Yeah. Now let's move on to the next one, electromagnetic induction. So far we have seen when electric current flows through the conductor, magnetic field is developed. So that kind of explanation we have seen. Okay, magnetic field because of electric current. Now electromagnetic induction, reversal of it. That means, shall we produce, is it possible to produce current with the help of magnetic field? That's what reversal direction. So this is explained neatly with some experimental things that's done by Michael Faraday. We are having Faraday's laws, Faraday's first law and second law we used to study it as, and that is what about inducing of the current. Okay, yeah, Lenz rule also there. Lenz rule will give the direction of the induced current actually. Faraday's first law, second law we will discuss, and then Lenz law will come. Okay, so fine, whatever. Electromagnetic induction states that it's the phenomena of inducing the current in a coil or in a conductor due to the change of magnetic flux linkage with the coil. See here, the phenomena of inducing current in a conductor due to change in magnetic flux linkage associated with it. So this is what we are calling it as electromagnetic induction. By this time you have understood what we are going to extract in this one, that is inducing the current. When electric current flows through the conductor, we have talked about magnetic field. Now by using the magnetic field, can't we generate the electricity? Can't we produce the electricity, electric current? Yes, we can produce. That's what we are saying it as Faraday's first law. When magnetic flux linked with the conductor changes, then EMF will be induced. That EMF will be directly proportional to rate of change of magnetic flux. Those are Faraday's first law and second laws. The direction of the current is given by the Lenz law. What is that Lenz law? Direction of the induced current is just opposite to the cause of producing it. That means induced EMF. So Faraday's first law, second law and Lenz law. Hope I am clear to you. Okay. So see here, phenomena of inducing current in a conductor due to change in magnetic flux linkage associated with it is called electromagnetic induction. So see here, in this particular case, suppose if I take a coil, if I say, in that, so this coil, that it is connected to a galvanometer to show the direction. Okay, now if I bring this magnet towards this coil, then whatever the magnetic flux linkage or magnetic flux that is associated with this conductor will be changing, then current will be induced. So what is the proof to identify? Yes, so there is a galvanometer here. This galvanometer will be showing the deflection. Very simple. When will galvanometer will show deflection? When there is a flow of electric current inside the conductor. If there is no conductor, if there is no current, it won't show any deflection. So I have kept the coil here stationary and I have brought this magnet into this, towards this coil. Then what happens? This galvanometer has shown the deflection. So it means what? It means current is induced in the coil. This is what we are calling it as electromagnetic induction. Electromagnetic induction. Phenomena of inducing current in the conductor due to changing the magnetic flux linkage associated with it. That's what we are calling them as Faraday's laws. Faraday's first law states that EMF will be induced when magnetic flux linkage is changed, which is associated with the coil. Second law states that induced EMF will be directly proportional to rate of change of magnetic flux linkage. And the direction of the induced current can be given with the help of Lenz's law. That is, induced current direction is directly proportional to the, it's in opposite direction to the cause producing it. That's what we are studying it as E is equals to minus N d phi by dt. Now anyhow, that expression and all you are not having, you learn in class 12. So here this simple experiment activity says that electric current is induced in the coil when this magnet is brought near the coil. That's phenomena nothing but electromagnetic induction. Hope I am clear to you. Phenomena of inducing current in the conductor due to change in magnetic flux linkage associated with it. Alright. And one more thing. This is one activity, one sort of producing the current inducing the coil. Another way also there. In this case, I kept coil stationary. I brought magnet towards the coil. Another case you take. You keep magnet stationary. Now bring coil towards the magnet. Then also magnetic field will be changed. See, our requirement is to induce the current. How current will be induced? Magnetic field if it is changed with the, that is associated with the conductor if changes. Alright. So further, whether you are keeping conductor stationary and coil if you are bringing, magnet if you are bringing, or keeping magnet stationary or coil if you are bringing, or if you are bringing both towards each other relatively, no matters. Magnetic flux linkage changes, yes, electric current will be induced in the coil. That phenomena only magnetic induction, electromagnetic induction. Alright, hope you have understood this magnetic induction. Aryan, have you understood? Sir, where are you from? Yeah, I am from practically. It's located at Hyderabad. Yeah, Aryan, have you understood this? Electromagnetic induction. Okay, fine then. Let's move on to the next one. Yeah, Fleming's right hand rule. So here, earlier Fleming's left hand rule we have seen. Okay, now Fleming's right hand rule. That right hand rule is to know about the direction of induced current. See, current is induced in the coil, right? How can you find the direction of induced current? Yes, here is the solution. I mean, that's direction can be obtained with the help of Fleming's right hand rule. We have seen FLR previously. Now this is FRR, Fleming's right hand rule. Okay, hope this screen is clear to each and everyone. Okay, fine. Yeah. So Fleming's right hand rule states that stretch the first three fingers of the right hand mutually perpendicular to each other. Say the thumb finger, forefinger and center finger like this. Okay, so if you stretch the first three fingers of the right hand mutually perpendicular to each other in such a way that by pointing the forefinger along the direction of the magnetic field, same previously, and thumb finger along the direction of motion of the conductor, then the direction of the induced current is given by the center finger. I said the word induced current since the current is induced by the phenomena what we are calling it as electromagnetic induction. Okay, so this is how FRR you can apply, Fleming's right hand rule. Stretch the first three fingers of the right hand mutually perpendicular to each other in such a way that by pointing index finger along the direction of the magnetic field, thumb finger along the direction of motion of the conductor, then the direction of the induced current in the coil or conductor can be given with the help of the center finger. That means center finger represents the direction of the induced current. FRR, very very simple. Okay, so here Fleming's right hand rule, FRR, field is represented by forefinger or index finger. Okay, next thumb finger, sorry, motion is represented by thumb finger, then induced current is represented by center finger. Okay, alright, so in this one now we have discussed electromagnetic induction, right? There is an activity, simple activity. If you take any, let us take a paper cylindrical roll on which two coils, say coil 1 and coil 2 are wrapped like this. Okay, let me draw this again like this. Okay, this is coil 1, this is coil 2, which are wrapped on a paper cylindrical roll, which is a non-conducting material, and but this coil 1, coil 2 are placed side by side. If you look at the diagram here, coil 1 is connected to a voltage source, say battery, whatever, and coil 2, there is no voltage source in the coil 2. It is connected, it is just closed with a galvanometer. Now when the electric current is passed through this coil 1, then you can notice the direction of the the deflection of the needle is the needle in the galvanometer has shown the deflection. So what does it mean? There is no direct connection, of voltage source to this coil 2. Just because of the current that is flown in its neighboring coil, the deflection has shown in the coil 2. Point number 1, deflection is shown means current has flown, that's all. When there is no flow of electric current, then galvanometer won't show the deflection. So here coil 1 and coil 2, clearly you can see there only the voltage source connected to coil 1, no voltage source in coil 2. But still when current flows in coil 1, Coil 2 also has shown the deflection. The galvanometer connected to coil 2 also has shown the deflection. So when electric current flow in the neighboring coil, that means in coil 1, in coil 2 also current is produced. This phenomena we are calling it as mutual induction. So mutual induction is nothing but the phenomena of inducing current in a coil due to the flow of electric current in its neighboring coil. There is no direct voltage supply to the coil 2, but still just because of flow of electric current in the coil 1, in coil 2 also electric current is induced. This phenomena we are calling it as mutual induction. All the transformers which you are seeing, transformer will work on the principle of mutual induction. Okay, fine. So okay, this is about mutual induction, electromagnetic induction, and Fleming's right hand rule. Now let's move on to next topic, electric generator. Yes, interesting topic. Yeah, so electric generator, electric motor we have seen, and now this is the time to discuss electric generator. Electric generator is an electric device that can convert mechanical energy into electrical energy. Okay. It converts mechanical energy to electrical energy. It works on the principle of electromagnetic induction, the same principle which we have discussed. What is that? Magnetic flux link with the or associated with the current coil, associated with the conductor changes, then current will be induced in the conductor. I repeat, if the magnetic flux linkage with the or linked with the conductor changes, then current will be induced in that conductor. So that's what we are calling it as electromagnetic induction. It works on the same principle. So here also that arrangement consists of strong magnetic field. So to represent the strong magnetic field, I have taken the poles of the horseshoe magnet, where the direction of the field is directed from north to south here, and here I am taking an armature coil, that's nothing but ABCD here in representation. Here sorry, just a minute. Okay, here this is all right. Yeah, so here are the brushes, okay, and that's connected to an axle rod here. Okay, anyhow, in the examination will be you can sketch with the help of this instruments, so you don't face any kind of problem. Connect it with the help of connect it to a source like this, okay, and here slip rings will be there. Okay, now if you see the labeling here once, let the coil, this is A, B, C, D, that, okay, right, these are slip rings. Here brushes B1, B2 carbon brushes. This is okay, sorry, voltage source, no voltage source here. to represent to indicate what current flow, just a galvanometer you can take. Okay, so it's a very simple arrangement. Electric generator is a device that converts mechanical energy into electrical energy. We are giving mechanical energy as input. So for that I am just using an external source, that's called what I can say, an axle rod here. Here two things here, either you can rotate this axle rod just by applying some external force, or use any simple or any other kind of circuit also to run it by using less effort. Okay, if you want to rotate it on your own, means you have to apply more amount of force on it, more effort. So simply you just want to run it with the help of any kind of any other mechanical advantage or electrical advantage, use another additional simple circuit for it. Okay, fine. So this arrangement consists of a magnetic field which is produced by the strong poles of the horseshoe magnet, and an armature coil ABCD which is connected to a galvanometer with the help of conducting brushes, carbon brushes, as well as slip rings. Through the slip rings you can find out the axle rod over here. This axle rod is just, again I am saying, just to rotate the coil. It helps out to rotate the coil. Since here the coil should be rotated, then only the magnetic flux that is linkaged or associated with the coil changes. As a result, EMF will be induced. That's what we discussed. It has Faraday's laws. Okay, so here magnetic field is directed from north to south. I am here you should apply Fleming's right hand rule, don't forget. So I am keeping my forefinger along the direction of north to south. All right, and now say this coil is started moving in clockwise direction. That means like this. Okay, so here if this is the coil, just as I have addressed in the previous motor, if I say this is the, what I can say, this is the coil, sides A, B, C, D, just take a book and hold in your hand like this. Okay, just like that you can find out A, B, C, D. Okay, now this has to make the rotation clockwise. So clockwise means this AB has to come upward, AB side has to come upside, and when AB comes up, CD goes down. Now you have to apply Fleming's right hand rule to find out the direction of the current induced in it. Okay, fine. So very simple. I am directing this right hand in this FRR, point the direction of the magnetic field with the help of index finger, just like this, north to south, and AB comes upward. So motion is in upward direction, force is experienced in upward direction. So keep this forefinger upward. Then how the index finger, see this is the index finger direction, how it is showing? It is showing towards this, which means if I take, this is the coil here, armature coil here, if I apply here, this is the what? Field direction, and this edge is moving up, it's moving up. So along this edge current is induced, which means towards AB, like this, AB, BC, CD. So it's A to B, B to C, C to D, and from B2 to B1, A, B, C, D, B2, B1, A. This is the direction of flow of current in the first rotation of the coil. Okay, so now AB comes upward and CD downward. Already when you are rotating it, the remaining half rotation, if you check, AB come downward, and AB come to this side, CD comes to this side. Now how the direction of current will be? It's very simple. If CD comes this side, D, C, B, A, now B1, B2, D. So it is just opposite to the direction of current that is flowing in the first half rotation. So for every half rotation, electric current that is induced in the coil is changing. So then final output of the output wave of the electric AC, if you see, you will get like this. Okay, voltage and time graph if you see. So what does it indicates? That For every half rotation, direction of the current induced is altered. As the direction of current induced is altered, we are calling it as the alternating current. Alternating current. That's what AC. It's not AC current, it is AC, alternating current. DC, direct current. In direct current, there is no change in the polarity. There is no change in the polarity. The direction of the constant is, the current is constant with irrespective of time. But here it is not like that. For every half rotation, direction of electric current induced in the coil will be changing. For every half rotation. Okay. So that what happens then? This is how the voltage output will be, which we are calling it as alternating current. So we'll get the frequency of alternating current that which we are using is 50 Hz. 50 Hz frequency. Okay, so that's how you can explain the working and construction and working of electric generator. So simple children, electric generator is a mechanical is an electrical device that converts mechanical energy into electrical energy. So we are giving that input to this rod, axle rod. Axle rod is mechanical element. We are rotating it. We are rotating axle rod, and which is attached to the armature coil. As a result, coil also rotates. So it means you are giving mechanical energy as input to the system. To the device you gave mechanical energy as input. Then here this conductor is started rotating in the presence of magnetic field. So when the conductor is rotated in the presence of magnetic field associated with the conductor changes. When magnetic field associated with the conductor changes, by using the Faraday's laws we can explain what will happen. EMF is induced, nothing but electric current is flowing inside the coil. So that is what the principle behind it, electromagnetic induction, which we have learned just now. Phenomena of inducing the current inside the coil due to the change in the magnetic flux linked with it. So then this when it is rotating here, for every half rotation current direction is altered here. As a result, the polarity of the current for every half cycle is altering, and this is how the wave output waveform of the induced current over here. And then that's why we are calling this current as alternating current, which has a frequency of 50 Hz. Whereas direct current, if you take, there is no frequency for it, since the direction of the current for DC is same, it's constant, it won't alter. As a result, frequency is 0, no cycles, nothing else. Okay, fine. This is about electric generator. Right then, and the last one, domestic circuits, very simple. So the circuits, the powerhouse, what we are having, the electric current which we are receiving it can be utilized especially in domestic circuits in two ways. One is for 5 ampere circuit, another one is 15 ampere circuit. These are the two power circuits which we are having in the domestic purpose. 5 amp circuit is for using the light objectives, such as light in the sense what can we say, such as fans, lights, small objects, objects we can say, not in terms of small and large in terms of size. It depends on what the consumption, consumption of electrical energy. If they are consuming very little amount, so we'll segregate it as 5 ampere one, 5 ampere power circuit. Heavier one, such as geysers, air conditioners, motors, okay, washing machines. So those and all will operate under high power circuits, that will be operated under 15 ampere circuits. So okay, whatever, generally we will take it from the electric supply, we will take from the outside supply we will get. So this supply will be connected, given to the mains here, and from here two wires we will take. One is live wire, other one is neutral wire. I am representing all with the same colors, and I will name it over here. So live here, this is neutral, live I am taking here, neutral I am taking here. Okay, so here I'll mention here again distribution box also. So from here 2 or 3 device I'll mention here, leave it. Okay, yeah. So you can see that three plugins, 3-pin socket here. Here, this one first, suppose if I say this is a live wire and this is a neutral wire. Live wire, we can also call it as phase wire. This is basically should be represented with red color. Neutral wire will be represented with black color. Okay, and here the third plug is there, no, third one, third place, that can be named as what? Earth wire. So live, neutral, earth or ground wire. Okay, so like that it will be connected. All right, so here this ground wire will be in green in color. Domestic arrangements, see here children, from the main, from the supply, from the transformer we'll get the input supply to the mains here, and from the mains we'll connect it to the distribution box, and in fact over there fuse system will be there. From the distribution box we'll segregate into two things. One is 5 ampere circuit, another one is 15 ampere circuit. Under 5 ampere circuit, the objects which will having low consumption of electrical energy will be used, such as the bulbs, fans, etc. And under 15 ampere power circuit we can be having heavier amount, higher consumption of electrical energy devices such as air conditioners, motors, geysers, etc. And over here mainly this can be operated with the help of these two wires. I can say ground is optional, but if you are having ground, that can be just like a protecting one. Okay, which can send excessive currents to the earth, like protection purpose. So here live wire is represented generally with the help of red color. Live wire is also called phase wire. Okay, and then neutral wire is of it's represented in black in color, and then green wire, green color, green is what? Ground or earth, I can say. And here when this live wire and neutral wire will be direct contact, they will come in direct contact, then short circuit will occur. Under short circuiting, what will happen? Abnormal current will flows that. So as a result, all the electrical devices, or the even entire household things may catch fire. Very dangerous. So to prevent that short circuiting conditions, we are having that in the near the distribution box, near this mains arrangement itself, we are going to use a safety device called fuse. Okay, so fuse is made of a low resistivity material and low melting point, which is a combination of an alloy called lead and tin alloy. When excess current flows through that circuit, then it will be melted out by default. Okay, so as a result, that can prevent all other electrical appliances. So that is how we can prevent it from the short circuiting conditions. When short circuit will occur, when the phase wire and live wire will come in direct contact, then short circuit will occur. One more thing is there here, overloading. What is meant by overloading? Overloading is nothing but, suppose there is one socket which we are going to do usually. Okay, many times even you might have done. There is one socket over there and you want to use one mixer or another different electrical devices at a time. Then what will we do? Only one socket is there, so we will connect any spike cord or else any what I can say plug box. Okay, we will keep over there, and this plug box or spike cord will be having multiple sockets, but it's ultimately operated under single socket only actually. But you are connecting here multiple devices simultaneously. As a result, what will happen? Under single socket, when you are operating many more devices, more than one device, then it leads to the occurrence of overloading. Overloading, very very important one. So overloading is nothing but the situation when will occur, children? When multiple devices are operated under single socket simultaneously, then overloading will occur. So this is about domestic circuit, children. In this mainly you have to remember about this diagram, as well as live wire, or you can also call it as phase wire, can be represented red in color. Neutral wire is represented black in color. Ground wire or earth wire can be represented green in color. Two power circuits that are there in our domestic circuits is 5 ampere and 15 ampere circuits. Under 5 ampere light consumption objects, and 15 ampere heavier consumption of electrical objects, electrical devices you can operate. And when a phase wire and live wire, phase wire and neutral wire will come in direct contact, short circuit will occur. To prevent short circuit, to prevent these devices from excess current, we can have safety device, so-called fuse. And when all these devices are operated under single socket simultaneously, then overloading will occur. This is about domestic circuits. Okay. Yeah. Hope the session. Hope you have understood the content, the concepts in one shot. Just why we named it as one shot, we just tried to complete all these things in a single session. And with this today's session, physics I have completed, electric current as well as current electricity as well as magnetic effects of electric current. Similarly, even mathematics as well as biology also available just as one shot in the practical YouTube channel. Just download the app and follow the YouTube channel of from the practical year. Okay, fine children, I am signing off for today. Thank you.